Okay, let's talk about reaction rate and collision theory. So reaction rate, or rate of a reaction, is just the measure of how fast a reaction occurs. And how fast a reaction occurs is going to be affected by things like the reactant concentration, the surface area of the reactants, the temperature, if there's a catalyst present. So there's lots of ways that you could manipulate the rate of a reaction. You could get it to go faster by changing these things, or possibly slower by changing these things. So a particular reaction at a certain set of conditions naturally has a specific rate that it occurs at. But you can change that by changing the conditions. But every reaction is different. So every reaction has kind of its own natural rate, but we can manipulate them. And we're going to look at, why these things affect reaction rate. And really, this is all explained by collision theory. So the basic idea of collision theory is that it tells us that the collisions that occur between your reactants need to occur with the proper orientation and with sufficient energy. Okay. So in order for these reactants to react, of course, they have to collide. They have to come together. If they don't come together, they can't react. Okay. So I guess you could also say that's part of collision theory. You have to have a collision, but those collisions need to meet the criteria of having the proper orientation and having sufficient energy. So let's talk about those two things a little bit more. When they say it needs the proper orientation, that means that it needs to have direct contact between the atoms that need to form bonds. Okay, so in a reaction, typically there's some breaking of bonds and forming of bonds. Okay, and the breaking of bonds, that could just happen on its own or because of a collision. But to form a bond, you have to have those atoms come together. They have to come into contact so that they can form a bond. And when we say it needs the proper orientation, well, that means you need to have the atoms that need to bond come together. Okay, so here's an example reaction. We have O3, which is ozone, reacting with NO, or nitrogen monoxide. And it forms oxygen gas and nitrogen dioxide gas. In this reaction, if you look at what's going on, at a minimum, you are breaking an oxygen-oxygen bond and you're forming a nitrogen-oxygen bond. Okay. Now we're not worrying about breaking bonds because, like I said, breaking bonds can happen due to any kind of collision or just simply because that molecule, ends up breaking it down because it's unstable at that point. And so the important part is the forming of bonds. So we need to form an NO bond to convert the NO to NO2. And so if we think about some possible collisions between O3 and NO, you could have it collide to where the oxygen of the NO molecule reacts with the O3. But if that happens, then you're putting an oxygen in contact with another oxygen. But we don't need to form another OO bond. We need to form an NO bond. So that would not have the proper orientation. So even though you probably have lots of those collisions occurring in the sample, in the reaction mixture, those collisions don't do anything. Okay, so it's not a successful collision because it does not have the appropriate orientation. Whereas if instead that O3 molecule collided with the nitrogen end of the NO molecule, then it is putting in contact the nitrogen and an oxygen from the O3. And so it is putting those atoms that need to bond together in contact. Okay, so that collision does have the proper orientation, meaning it has a chance of being successful. Okay, now you have to be careful. Proper orientation is not the only thing that is needed. Okay, it also needs sufficient energy. So even though you have those collisions with the proper orientation, it could collide and still just bounce off and nothing happen. Okay. Now, the first one without the proper orientation, it's always just going to collide and nothing happens. Okay. But the second one, it has the appropriate orientation. So sometimes when that collision happens, you're actually going to get the new bond form and that oxygen release from O3. And other times it's just going to bounce off and nothing happens. Okay. And that all depends on the energies of these things. So does that collision have enough energy to form that new bond? That's what determines if it ends up being successful. But you can't have a successful collision that forms these new bonds without the appropriate orientation. Um, but like I said, the other thing is it does need the sufficient energy, meaning your collisions need to have enough kinetic energy so they can break what bonds need broken and form the new bonds. Okay. Now, occasionally they don't need to actually break some bond, but they still need to collide with enough energy to where they will form kind of an intermediate to get to the product. And so the energy needed, or, the energy of that collision that things need to have is the activation energy. Okay, that's the term that is used to describe the energy needed for that collision, or that the collision needs to react. And so sometimes it's written as EA, that's activation energy. And so when you think about the activation energy, what you need to realize is that is specific to a reaction. Okay, each reaction has an activation energy that is related to, the structures of the reactants and products, and essentially how difficult it is to convert those things. And so when you have a reaction that has a higher activation energy, that in general is a slower reaction. Okay, because on average, the collisions aren't going to have enough energy. Okay, they're not going to reach that activation energy if it's really high. Okay, whereas if you have a reaction with a low activation energy, then that tends to be a faster reaction because on average, the molecules or atoms, whatever, have enough energy to achieve the activation energy. And so I keep saying the average energy of these reactant molecules or atoms. So you have to remember that when you have a sample of something, the temperature relates to the kinetic energy of the substances in that sample, right? But even though everything in the sample is at the same temperature, they don't all actually have the same kinetic energy, because what happens is that kinetic energy is related to the motion of those molecules, how they're vibrating within themselves, and how they're moving within space. And what happens is when they collide with other molecules, sometimes some of their kinetic energy may be passed to the other molecule. So one of them could leave the collision with less kinetic energy and one can leave with more. So they end up having different kinetic energies. And so as collisions happen, that energy gets passed. And so on average, the kinetic energy of the particles in a sample is related to the temperature. Okay, so the temperature tells you about the average kinetic energy, meaning that there's some molecules that have that energy, some have less, and some have more. Okay, so when you have molecules that have enough energy, to reach this activation energy in a collision, those will react. But ones that at a given time don't have enough energy, the collisions that they make won't have enough energy, and so they won't react. Okay, so within a given sample, not everything has the same energy, or it has the same kinetic energy. So then those collisions aren't going to all have the same energy. And so when we have these collisions, you need to have your proper orientation and you need to have sufficient energy. But if they either don't collide right or don't have enough energy, then the collision doesn't matter, essentially. It's not successful. Okay. So it could be that you meet one or the other of the criteria, and if you don't meet something, then the collision's not successful. Okay. So if it's not in the right orientation, it doesn't matter what the energy is of these things colliding. It won't be successful. Or you could have things that have enough energy, but if they don't collide right, then it still doesn't react. But if both of those things are true, then you're going to have a reaction. Okay. But within a sample, some of the molecules aren't going to have as much energy. So some of them will react, some of them won't. And so that's where you'll hear them talk about a portion of successful collisions. So a successful collision is when the reactants go to products. Okay. But not all of them will, because whether or not these criteria are met or not. Now, when you do have a successful collision, what actually happens is there is an intermediate formed. It is a short-lived intermediate, so meaning this forms and breaks down very quickly. Okay, and so it's that intermediate that's formed is usually called an activated complex or a transition state, and that is kind of a connection of the things that are colliding. But as the new bond is forming, connecting those things, you also have some bonds breaking. And so that's why this is a short-lived intermediate. It, for a very short time, is kind of connected, but it very quickly breaks apart now into the products. And that complex has that high energy that is equal to the activation energy for, or it's the difference between the reactant energy and the activated complex energy is your activation energy. Okay, so it is higher energy than the reactants. Okay, now let's see. I was saying at the beginning that there's several things that we can do to manipulate the rate of a reaction, right? There's several conditions that can affect the reaction rate, so we can manipulate how fast a reaction goes. And let's relate those things now to what the collision theory is predicting about reactions and how they occur. So one of them was reactant concentration. This is a pretty common one. This is a pretty easy thing to change. We can just add more reactant or start with less reactant and change how fast a reaction goes. Now, why is that? Well, if you add more reactant or increase the concentration of the reactant, then you're going to get more collisions because there's more stuff there. Okay, so there's more stuff in a given amount of space. And if there's more stuff moving around in that space, it's going to run into each other more. Okay, so you have more collisions. If you have more collisions, you're going to have more collisions that have a proper orientation. Okay, and so if you have, 1,000 collisions instead of 100, then in total you're going to have more with the proper orientation, because those extra 900 collisions aren't all going to be with the wrong orientation. Statistically, you're definitely going to have more with the proper orientation. And so that's actually why it speeds up the reaction, because just by chance you're increasing your chances of colliding with the appropriate orientation because you're having more collisions. But what you need to realize is the fraction of successful collisions stays the same. So when I say fraction of successful collisions, maybe it's easier to think about saying percentage of successful collisions. So the same proportion of things are successful. So if initially 50% of the time the collisions have the appropriate orientation, then if you throw in more molecules, then it's still going to be 50% of the time. So if we use that scenario of first we did it with 100 molecules and it's 50% successful, that means 50 collisions out of 100 would be successful. But if we upped it to 1,000 molecules, now we have 50% of 1,000, so 500 successful. So we did increase the number of proper orientation collisions, but the fraction or that percentage that is successful remains constant. Okay, so you can't increase it in that way, but you can just throw more stuff at it and your chances are higher of getting a proper orientation. Okay, or you have more of them, I should say. Now, another condition that can affect reaction rate is surface area. Usually, or really, this only comes up when you're talking about solids. So if you have a solid that is being reacted with, if it's all clustered up, then you just have the surface area of that that can be collided with and react with things. But if you were to crush that up and spread it out, you'd have more surface area. And so there's more things for it to collide with, for the other reactants to collide with. And so you would have more collisions in that case. So if you expose more of the reactant, if you free it up so it can interact with things, you're going to get more collisions. And again, if you have more collisions, there are going to be more that have the appropriate orientation. But that fraction of successful collisions, so the chance that they collide in the right orientation is going to stay the same. Okay, that will not change. Because the fraction of successful collisions, that in part is due to the structure, and you're not changing the structure. Okay, so the complexity of the molecule, the more complex it is, the less likely they're going to collide just right. But it also has to do with the energy of those collisions, because in order to be successful, they need enough energy. Okay, and so that's where one of the other conditions comes in that we can change. We can change the temperature of the reaction, so we can increase the temperature or decrease it. If we were to increase it, we would be increasing the kinetic energy that the reactant molecules have. And so they're moving faster, okay? And if they're moving faster, you're going to have more collisions again. So that's another way you can increase the number of collisions. And so you've got more collisions. And so if you have more collisions, you're going to have more with the appropriate orientation just because you have more collisions. But you also have an increased fraction of successful collisions, and that's because the energy changed, okay? Because on average, you have more molecules that have a high energy if you're at a higher temperature, okay? Meaning you have a higher proportion that have enough energy to meet the activation energy requirement when they collide, okay? So changing the temperature tends to have a bigger impact on your reaction rate than the others, okay? So that one, you know, it's pretty easy to do, and you're going to get more benefit out of it. The drawback of changing temperature of a reaction is sometimes the reactants or even the products can't handle it. And so if you have, you know, reactants or products that are very temperature sensitive, so if you increase the temperature, maybe they decompose, then you have to rely on other ways to change the reaction rate. But changing temperature, that's a really easy one. That's a common way people speed up reactions or slow them down. And then changing the reactant concentration. The surface area, that really only applies if you're dealing with solids, which most of the time we're dealing with aqueous type reactions or gas phase reactions. And so that wouldn't help you on those. And let's see, the other thing that I had on the list was catalysts. Um, but I don't have it listed here because a catalyst, if you add a catalyst, it speeds up the reaction, but that's it. Either you have a catalyst or you don't. So either it's going at the rate of without the catalyst or it's going at the rate with the catalyst. Okay. And typically the reason a catalyst is going to speed up the reaction is because it helps more collisions collide with the appropriate orientation. Okay. So that's where it helps. It also can change the energy of the intermediate, just because it's a different intermediate. So that's a little bit different. We'll talk about that in another video a little bit later.